Hey everyone, here we are at the beginning of Unit 2 of Math 2. And the idea of this unit is to explore more on this idea of the parabola and what kind of function makes that parabola. Now we know that a linear function can be written so that it's y equals mx plus b, or y minus k equals m times x minus h. We have different forms for a line. Well, we also have different forms for a quadratic, but the point for this unit is going to be totally focused on the vertex form, and so how that function with numbers and letters relates to the graph, the parabola that we were introduced to last unit. Okay, so this lesson is really focused on just exploring some relationships within that equation so we can start seeing some basic things in our graphs of parabolas. And so just like you're able to graph a line by identifying the y-intercept and identifying the slope, or by identifying a point and a slope, we're going to be able to graph a parabola by identifying the vertex and its slope pattern. So with that said, that's kind of our goal. The idea is to determine a function type based on its equation. Okay. Anyways, let's go ahead and take a look at a relationship using tables from the two equations that we see here, y equals x and y equals x squared. So looking at this first one here, we got y equals x. You guys should be able to recognize that as just a line, right? It's just a line with a slope of 1 and a y-intercept of 0. But we want to go ahead and fill out this table just for good practice to get an idea of what's going on. So for the equation y equals x, we have this table that we created, the xy table, and we have different values, -2, -1. Oops, my line's really bad there. 1 and 2. So when I go ahead and plug in -2 to x, the idea of the table is to figure out what the y value is as a result of this. Well, if x is -2, then y is going to be -2 also, because it says y equals x. In fact, in this particular case, whatever I plug in for x, I get out for y. Okay? So that's that. Now, if I was to graph this, these points, plot these points, -2, -2 is this point right here. -1, -1 is this point. 0, 0 is here. 1, 1's there, and 2, 2's there. And we can keep going with that, but we can see that we have a linear equation. We have a function, a linear function, with a slope of 1 and a y-intercept of 0. That's exactly what this says here. If I rewrote it as y equals 1x plus 0, that would be equivalent to that. And those are the same equations. So we use that as a foundation for graphing linear functions, okay? Now, let's transition into the quadratic functions, where we have y equals x squared. Well, if I were to create this table, and I'll try and be a little bit straighter with my lines here. If I were to create this table, x and y, and we have -2 there, -1, 0, 1, and 2. I'm going to show some work here because I want to be very careful about how I do this. If I plug in -2 to x, well, maybe I'll go off to the side here so we can see this. If I say -2 squared, because that's what the equation was, it was x squared. Remember, anytime you do substitution, you plug in, when you plug in that number, you put parentheses around that number. That helps us identify what we should do with it. So -2 squared really just means -2 times -2, which is +4. So going back to the table, we end up with 4 here, okay? We do the same thing on the other one for -1. So -1 squared, well, that's -1 times -1, which is just 1. And then plugging in 0, I'm not going to do that. 0 squared, 0 times 0 is 0. And then 1 times 1 is 1. And then 2 times 2 is 4. So you can see this pattern here, right? And we should be able to recognize what type of function this is based on what we did last unit. Let's check our first differences here. Well, we can see that we went down 3, we went down 1, we went up 1, we went up 3. Okay, so it's not linear because those aren't the same. The first differences aren't the same. The next one, well, we went up 2, then we went up 2, then we went up 2. So we can say, based on this graph here, or based on this table, that this is a quadratic function since the second differences are the same. Okay, so that is what we learned last unit. And we also learned that if that's the case, then we get that U shape, that parabola shape, okay? But we're going to go more in depth with that. So let's go ahead and graph this parabola and see some interesting features about it, okay? So here we have the coordinate -2, 4, so that means we go back 2 and up 4. For -1, 1, we go back 1, up 1. For 0, 0, it's the origin. For 1, 1, and for 2, 4 there. 2, 4 is over 2, up 4. And so we have this parabola here based on those 5 points. Now we can add more points to it. We would just have to expand our table so it includes those. And hopefully you can kind of see pretty quickly that if I put a 3 here, well, 3 squared is 9. That's over 3 up 9. That's way up here. I'm not going to graph that, but there's our parabola, okay? Now, when I compare the two functions, what I do is I call these the parent functions. These two functions are the functions that every other function within their families are based on. This is the parent linear function, y equals x. When I change the slope in front of it, that changes the steepness of the line. And when I change the y-intercept, in this case 0, that changes where the line starts, okay? Same thing here. This is the parent function for a parabola. Y equals x squared is the parent function, and all other parabolas are based on this function, y equals x squared. We've got the vertex here, and then we're going to talk about a slope pattern in a little while. So just real fast, we did those tables, so I'm just going to fill those in. And again, we can see the first one's linear. If we check the first difference, we would see it's linear. And the second one, check the second difference, it's quadratic. Okay. But let's go ahead and take some notes on this. Parent function, we just kind of talked about it briefly just now. The parent function, y equals x squared, is a parabola, okay? That is the parent function of a parabola. So graphing that, y equals x squared, this is the exact same graph that I just did on my work over here, okay? We would say this: every other parabola is created by reflecting, by stretching, and by translating the parent function. So essentially, if I take this parabola, I can shift it up, I can shift it down, I can shift it right and left, okay? That's a translation. I can reflect it, which means instead of it looking like a U that opens up, it could be upside down, so it opens down, so maybe it looks like an N or something, right? Something like that. So I could reflect it. And then I can stretch it, so I can make it kind of skinnier or wider by taking these points and stretching them up or pushing them down, okay? So every other parabola is a result of the parent parabola, or the parent function y equals x squared, okay? And we've talked about, I don't know if we talked about this, maybe we haven't. If the function's highest exponent is a 2, then the graph is a parabola, okay? So here's an example of that. If I say y equals 2x squared, we can see that the highest exponent is a 2. If the highest exponent is a 2, then it's a parabola. Y equals x minus 5 squared. Well, if I expand that out, x minus 5 times x minus 5, and then multiply all that out, the highest exponent would still be 2. So this is also going to be a parabola. And then another example, just real fast, we can see that the highest exponent here is also a 2. So it's a parabola. All of these numbers that are being added to it in one way or another will affect where this vertex is located, which way the parabola opens, and then whether it's stretched or shrunk, but it's all based on this parabola. So with that said, we're going to do some exploring here. I'm going to have you guys create some tables and things like that, and then graph the results of it. So in the first case, we already did this. Y equals, no, we didn't do this one. I'm sorry. This is y equals negative x squared. Y equals negative x squared. So let's go ahead and do this. And in fact, if you would like to pause the video and see what you can do on this on your own, that might be a good idea. And then when you think you got it, you can come back and compare your answers to mine. All right, for this table, notice the function is a little bit different than the function that I gave you before. This time there's a negative out front. Now we have to be careful with this because remember, technically that negative means that there's a -1 out front. And if we think of our order of operations say that we need to do the exponents before we do the multiplication. So when I go ahead and plug in -2, it's going to say -1 times -2 squared, like this. We don't multiply those first, we do the exponents first. So it'll say -1 times +4, which is -4. So then my y value when x equals -2 is -4. We can do the same thing with the -1. So -1 times -1 squared. We keep that -1 there, and we square that other -1. So -1 squared is 1, and that results in -1. Okay. For 0, that one's pretty straightforward. -1 times 0 squared. Well, 0 squared is 0, and then -1 times 0 is just 0. 0 times anything is 0, until you're in calculus. And then we can kind of do this in our head here. 1 squared is 1 times -1 is going to be -1. And then 2 squared is 4 times -1 is -4. So there we have the table there. And we want to plot those coordinates. We want to plot those points. So I'm going to come over here and I'm going to create my graph. And so there's my XY grid. The first coordinate is -2, -4. So I'm going to go back 2 and down 4. The next coordinate is -1, -1. So back 1, down 1. And then 0, 0. And then 1, -1, so right 1 and down 1, and then 2, -4, so right 2 and down 4. So we end up with our parabola. But in this case, you can see that our parabola opens downward. Okay. Now keep in mind when you're connecting dots, you always connect left to right. So you'll pick a dot and then connect it to the next dot to the right, then the next dot to the right, then the next one and the next one to get the proper graph. But what do we notice about this parabola? We notice that this parabola is upside down in comparison to some of the other parabolas that we've seen. This parabola opens down. Well, what's different about this parabola, this function, in comparison to the previous function we were dealing with? Okay, that's the question. Okay, now you can see that my graphs are way better on the actual lesson than my handwritten graphs. And so if you don't have perfect graphs, it looks a little messy, that's fine. As long as you're plotting those points in the right place, we're okay. So let's go ahead and write this down. This is very good, important notes for you. If in any parabola, y equals ax squared, if a is blank, then the parabola opens blank. Well, if in any parabola of y equals ax squared, if a is positive, then the parabola will open up. If a is negative, then the parabola will open down. We can see an example of that in what we just did as far as the work. Let me put these, well, let's see here. In our previous one, we had y equals x squared. The a value is the coefficient in front of the x term, the squared term. That's a 1. That's a +1. The a value is positive. We see the parabola opens up. Okay. Here we saw that the a value was negative, and as a result, we can see the parabola opens down. Are you ready for this? This is fun. The parabola opens up like a cup. The parabola opens down like a frown. Anyways, that's silly. All right, so looking at these graphs side by side in a nice, clean fashion, we can see, we can see that the two parabolas, we got the one that opens up, the one that opens down, and it's based on the a value in front. The a value is positive, opens up. The a value is negative, opens down. That's important. That's important. All right, let's go ahead and take a look at a little bit more exploration as we journey through our mathematical adventure here. Okay. It says, complete the missing pieces of the table and determine the indicated slopes for the graphs below. Now, this is going to take some time, so be patient with this, okay? I'm going to go ahead and minimize this because we're not going to need that for a little while here. So first of all, we want to complete the table. We want to figure out the y values according to the graphs. Well, when x equals 0, what is the y value? When x equals 0, the point on the curve is right here. What is the y value there? The y value is -3. When x equals 1, so that means we go to the right one, what is the y value? That y value is -2. When x equals 2, we go to the right 2, and then we go up 1 to get to the point on the graph, so that would be 2, 1. And then when x equals 3, we go to the right 3, and we have to go up to this point, so that'd be 2, 4, 6 to get to the graph. So there, we completed our table. Now, it says to find the slope over the interval 0 to 1. Now, we've done average slope in the past, so let's go ahead and look at that here. If I want the average slope from 0 to 1, that means I'm starting at x equals 0, so I'm starting at this point, x equals 0, and I'm going to the point 1, x equals 1. So I'll go ahead and do that work on here, but I'm also going to show you graphically what that looks like. So when x equals 0, what is the y value? Well, the y value is -3. And when x equals 1, the y value is -2, according to the table here. So we can just plug that into our slope formula, -2 minus -3 over 1 minus 0. And as a result, we end up with 1 over 1, or just 1. Okay, so that's how to do that analytically. We've had plenty of practice with that. But how do I find the slope in this interval 0 to 1? I find the slope from 0, x equals 0 to x equals 1. So I would have to go up 1 and right 1. 1 over 1, which is 1. Okay? For the next slope, 0 to 2, that means my first x value is 0, and my second x value is 2. So what is the coordinate at x equals 0? Well, we already have that. It's -3 again. What is the y value when x equals 2? The y value is 1. So we say 2, 1. And then we find the slope there. So it'd be 1 minus -3 over 2 minus 0. 1 minus -3 is 1 plus 3, so that's 4 over 2. So my slope is 4 over 2. Now, I could write that as 2, but there's a reason I'm not going to do that, because I'm looking for a pattern here. So I'm just going to leave it as 4 over 2. Okay. For the last one, we're looking for the average slope from 0 to 3. So 0 and 3 are my x values. Let's go ahead and find the y values. The y value is -3 for when x is 0. And the y value for x equals 3 is 6. So we find the slopes there. That'd be 6 minus -3 over 3 minus 0. 6 minus -3 is 9. 3 minus 0 is 3. And again, that can reduce to 3. But I'm not going to show that here in the lesson because I'm looking for a pattern, okay? So there's my example of what I want you to do. I filled out this first table and these first slopes. You guys go ahead and fill out this table here, and determine these slopes. And the goal is to figure out if we can see a relationship. So pause the video and see what you come up with. All right, with that said, let's see what you came up with. The x-coordinate, if the x-coordinate is 0, the y value is +1 here. When the x value is 1, the y value is 2. When the x value is 2, the y value is 5. And when the x value is 3, the y value is 10. Finding the slopes, doing it just like I did here, or looking at it graphically, you should have gotten 1 over 1, 4 over 2, and 9 over 3. Now, hopefully you really did that work, because if you did that work, you understand that you can see the relationship here between these. You can see that these slopes in this interval, or in this example, are exactly the same as the slopes in that interval. It's not that I wanted you to just copy these slopes. I wanted you to discover that through finding these values and determining these slopes. But that's something that's very important. That tells us that for every parent parabola, the slopes are based on a common relationship that they will be the same depending on something. And we'll talk more about that in another lesson. But we're going to focus specifically on this pattern for this type of parabola. Okay, so go ahead and write this down in your notes. In a normal parabola, I put that in quotes, in a normal parabola, the slope from the vertex to each point follows a 1, 4, 9 pattern. Well, let's go back just a second. A 1, 4, 9 pattern. Where do I see the 1, 4, 9? Well, I see the 1, the 4, and the 9 in the numerator, in the top part of the fraction. It follows a 1, 4, 9 pattern, okay? So go ahead and write that down, make sure that is clear. Now, I do want you to notice something because this is a beautiful relationship. 1, 4, 9. Where do those numbers come from? Well, we just kind of discovered it by creating those tables. But I find this very interesting. These are perfect squares. These are perfect squares. 1 is 1 squared. 4 is 2 squared. 9 is 3 squared. And so you should be able to come up with the next number in the pattern, 1, 4, 9. That's right, 16, because that would be 4 squared. So it'd be 16, 25, 36, 49, because it's 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared, 7 squared, and so on, okay? So that's an important thing. Why does that matter? Because we recognize the squares, these functions that we're dealing with are all dealing with x squared. That's the relationship. This is why it works, okay? So with that said, let's go ahead and take a look at an example. And I want you to graph the following using the y-intercept and the slope pattern. Now, I'm going to do this on my paper here. So I'm going to go ahead and cross this out and actually put the equation y equals negative x squared plus 2. Well, now I can create a table. I don't want to do that. I want to try and graph this as quickly as I can. What is one thing that I notice about this parabola? Well, the first thing that I notice is that the a value is negative, which means that this parabola is going to open downward. So I know that it's going to open downward. Just like in a line, if the slope is negative, that means it's going downhill, right? It's going to go downhill. All right. The second thing I notice is that it has a plus 2 at the end. And just like a linear function, that is going to be my y-intercept, at least in this very basic case. So that means I'm going to go up 2 on my y-axis and put a dot. Okay. Now from here, I'm going to follow my slope pattern that I just determined. Okay. Now notice the slope pattern is based off the slope from the vertex to each point that follows. Okay, from each point. So I have a slope pattern of 1, 4, and 9. What does that mean? That means from the vertex, I'm going to go down 1 and right 1. Okay? Down 1 and right 1. So 1 over 1. The next one is going to be 4 over 2 and 9 over 3. The next one would be 16, so it'd be 16 over 4. You can kind of see those patterns. We're basically squaring the denominator there to get to the numerator. 4 squared is 16, 3 squared is 9, 2 squared is 4, 1 squared is 1. But always from the vertex. So the first movement was down 1 over 1. We dealt with that one. The next one is the 4, so it's the 4 over 2. So we're going to go from the vertex, we're going to go down 1, 2, 3, 4, and over 1, 2. So we're going to put a point right there, okay? So we dealt with the 4. The next one is the 9 over the 3. So again, from the vertex, always from the vertex, it's down 1, 2, 3, 4, 5, 6, 7, 8, 9, and over 1, 2, 3. And so there's my point there. And so we can see that one. I'm getting a little bit long on my parabola here, so I'm not going to do that last one there. Okay. Now that's one half of the parabola. The other half is the reflection of that. So this point is 1 point away, or 1 unit away from the axis of symmetry. So I'll go another unit over here. Okay. This one's 2 away, so I'll move 2 over here. This one's 3 away, so 3 over here. And so now we can see our parabola starting to take shape very clearly. So we know it opens down, so this makes sense. So that works there, okay? All right, so I'm going to go ahead and put that on here, plotting that point, and then plotting the other points based on the slope pattern that we just described and just discovered. All right, now again, this is a negative a value, so it opens down. If this was a positive a value, I would start at positive 2, but instead of going down 1, right 1, I would go up 1, right 1. And then I would go from the vertex up 4, right 2 instead of down. That's the only difference between opening down and opening up. Okay, so that is an example of graphing a parabola. What I want you to do is practice by doing these two parabolas. So this is going to be the last two problems on the lesson. So go ahead and pause the video and see if you can graph these on your own. You should be using graph paper so that your graph is as perfect as it can be. And when you're done, come back and see how you did. All right, let's see here. Set up my XY axis there, pretty big. So what does this parabola tell me? What does this equation tell me? Well, first thing it tells me is that I've got to go down 5. So I'm going to go down 1, 2, 3, 4, 5, and I'm going to put a dot. That is my vertex. Then I'm going to follow my slope pattern. Notice the a value is positive, so I know that this parabola is going to open up. And my slope pattern is going to be 1, 4, 9, and so on. Again, that's a result of 1 squared, 2 squared, 3 squared. Or you could say this is 1 over 1 and 4 over 2 and 9 over 3 as far as actual slopes. So for the first movement, we're going to go up 1 over 1. And then from the vertex, we're going to go up 4, 1, 2, 3, 4 over 2. And then from the vertex, we're going to go up 1, 2, 3, 4, 5, 6, 7, 8, 9 over 1, 2, 3. And then if we needed to, we'd go up from the vertex 16 and over 4, but we don't need to do that. Now we'll reflect all those points to the other side. And then we can connect our dots and we have our parabola. Okay. Notice when I'm graphing my parabola, I'm not just trying to draw one straight line or one continuous line. I'm picking up my pencil and I'm kind of sketching it out back and forth. That gives me a little bit better of a curve. Okay. So that's the first one there. All right, let's go ahead and take a look at the last graph where we have y equals negative x squared minus 1. All right, well, when I go ahead and graph this, where do I start? I start down 1, negative 1, so I'm going to go down 1. Notice that's an a value. The a value is negative, so we know it's going to open down with that as the vertex. We just need to follow our slope pattern. 1, 4, 9, and so on. So remember, it's 1 over 1, 4 over 2, and 9 over 3. So we're going to go down 1, right 1, from the vertex down 4 over 2, and then again from the vertex down 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, and over 3. And then we'll reflect that about the y-axis there. And then we have our parabola. Okay, so that wraps up the concept. Let's talk about just summarizing these ideas so we know that we're in a good place. We have this parent function called, the parent function of a parabola is y equals x squared, and everything's built off of that. If the a value in front of the x squared is negative, here, let me use this. If the y value is the a value is negative, that means it opens down. If the a value is positive, it opens up. We start in these basic ones at a y-intercept of -5 and a y-intercept of -1 there. That's great. And then from there, we follow the slope pattern. And our slope pattern is 1, 4, 9, because those are results of perfect squares. So from the vertex, we're going to go down 1 over 1 or up 1 over 1. And then we'll go down 4 over 2 and down 9 over 3 from the vertex only. So that's a summary of how to graph a parabola, or a very basic parabola, from the parent function, and then shifting a little bit and things like that. If you have any questions for me, please comment or find me in a tutoring session somewhere, and I would be happy to help you out. Until next time, have a great night.